Okay, yeah, so last time I set the scene talking about, well, we talked about the cancellation of these singularities between the real and the virtual. And I didn't show it, but I said that this does happen, which seems maybe coincidental or fortuitous, but it is really, there is an underlying reason why one might expect it to happen. And the underlying reason is that actually, even at the level of the real diagrams, for example, there really is a factorization of the bit you associate with the long distance physics, the soft emission, the collinear emission, and the underlying hard process. And that allows this cancellation to happen, if you like. So let me say that. So I ended there. Let me draw a sort of schematic expression for the kind of thing we might want to happen. Cross section, d sigma, differential in whatever you're interested in. Quark collinear to the gluon, or indeed the gluon energy going to 0 here, equals d sigma q bar times some universal thing. Okay, and so that's the kind of idea. So if in that regime that happens, one can already see that it's more plausible that one might get a factorization, a cancellation of the virtual bit, which of course is also proportional to the q bar cross section. So this is indeed the case. So let's show it though. So this is indeed the case. Let's show it. So let's recall, first of all, the matrix element squared, which was proportional to this. Let me draw it all out again. SAB, call it that again, S13, S23. And let's investigate a little bit more. How this looks in the gluon. Let's say, in this case, why not goes collinear to the q bar? Of course, I could have chosen the quark. There's no particular reason, but just to take that as an example. So P3 collinear to P2. And so let's parameterize that in this way. So let's introduce a parameter Z, and let's say that we want them to be collinear. So P2 is going to equal Z times some momentum P, which just is arbitrary. It defines the direction of P2 and P3, but they certainly have to be collinear to each other. So in that collinear limit, one would carry Z of this P, one would carry 1 minus Z of this P2. So we're defining, i.e. P is just by definition the sum of the two vectors, okay? And indeed, you can see that therefore, these things are collinear, right? Slides up. So let's use that and see where it leads. So we've got, first of all, let's just remember, right? PA plus PB is equal to P1 plus P2 plus P3. P3, and that now we've just said is going to equal P1 plus P. Okay, so let's draw that just to be completely clear. There's PA, it's in a very schematic way, it's not a Feynman diagram, I'm just sort of representing the kinematics. And then P, remember, is P2 plus P3. Okay, and let's consider some of these variables and see what they look like in that limit. So PA plus PB all squared. Okay, well, that's equal to P1 plus P all squared, okay? Which is equal to, 2P1 dot P. And therefore, S, what I'm going to call S1P, according to the usual definition, is equal to SAB, or S, right? I'm calling that S, remember. Also, from the above, we've got PA minus PB, sorry, minus P is equal to P1 minus PB. That's just from energy and momentum conservation up the top, and we can certainly square those up. So let's do that. And therefore, rearranging that, SAP is equal to SB1. And similarly, SBP, oops, in the same way, just rearranging the above, is equal to SA1. Okay. In addition, we've got SA2, which is equal to 2. Remember, PA dot P2. We just substitute in our expression there for P2, ZP. Okay. That's going to be equal to 2Z PA dot P, which is equal to Z SAP, which from what we've just written above is SB1. And similarly, SB2 is equal to ZSA1. And finally, in just the same way, S13 is equal to 1 minus Z S1P, which is equal to 1 minus Z. Oops. 1 minus Z S. I've shown that up there as well. And we just substitute in. So therefore, in this collinear limit, what does our matrix element squared look like? There it is again. This goes to, so SA1 squared, let's go to that. So where is that? There it is. In fact, sorry, no, let's leave it as that. So SA1 squared, SA2 squared, that's what we're interested in. That's equal to Z SB1 squared. So Z squared SB1 squared. Then we've got SB1 squared again, and SB2 squared is equal to Z SA1 squared. So SA1 squared, there we go. And then on the bottom, we've got Z S as before, then S13, I've just told you is 1 minus ZS. So let me write that down. And finally, we've got S23, which we keep the same. That's the thing which is going to blow up in this limit, remember. So what's that? That's equal to, on the top, we've got a 1 plus Z squared factoring out. On the bottom, we've got a 1 minus Z factoring out. And then we've got a 1 over S23. Let me take that out, because that's the thing, as I say, that's blowing up, the 1 over it. And then we've got this thing out the front, factoring off. And what is that? That, when you go right back to really the first lecture, let me do that. Try and find where it is. There it is. Remember I mentioned that. It's just a QQ bar to QQ bar, two-body kinematics, U squared plus T squared over S squared. It's the QQ bar cross-section, amplitude squared. And in that language of SA1 and SB1, that is precisely U squared plus T squared. Okay. Just think about the two-body kinematics and what's the definition of U and T in terms of them. So that is equal to U squared plus T squared over S squared. Which, okay, up to some of course, proportional factors, alphas and so on, is certainly as claimed. And so there we have it, indeed. Something out the front times actually the QQ bar matrix element squared, and that's no coincidence, that's just a sign of this universal behavior. So including all of those factors, I've just sort of waved my hands about, including the GS squared in color and all of the rest, etc. We end up with when the dust settles, but really I've done most of the calculation above. In the Q goes to, or rather, we can also draw it like that. The Q bar goes proportional collinear to the gluon. That's the example I've given. So let me stick with that. And there it is. Now, and similarly, if the gluon became collinear to the quark, one would have a similar behavior. Okay, this is defined, just to be clear, in a limit. In the limit where these things are exactly collinear, 1 over S23 is infinite, so one has to, in the real calculation of showing this, be a little bit more careful of those things, but this is the basic idea. You know, as one approaches that limit, one of this starts to become true, if you like. So we define call it this, PQ to QG of Z. Remember, Z is the momentum fraction carried. Z is the momentum fraction carried of P of the quark, the antiquark in this case. 1 plus Z squared over 1 minus Z. That is precisely a splitting function, if you've seen that before. So this is the quark to quark gluon splitting function. So not too difficult to see just from that argument above that we're getting that behavior. So this is a universal object. Universal object that, you know, re-relates to that quark gluon collinear to a quark physics. So I'm being a little bit lax there. As I said, I started by talking in this specific case about the gluon being collinear to the antiquark. Hopefully it's clear enough to you that I could have done it with the quark as well and you get the same sort of result. So if I can, when I say things like that, I'm sort of interchangeably talking about either a quark or an antiquark. The idea is the same in this context. And this is the probability related to, one can think about it as the probability of emitting collinear radiation. That again. Okay. So we derived it for a specific QQ bar gluon case, but one can show that really this is universal. The fact that I've started, you know, here with this specific E plus E minus to QQ bar and then considered the gluon in that specific process, so QQ bar gluon becoming collinear, really wasn't the point. The point is this, as I say, these things are universal. One could consider any process of this type, and it's, as soon as you go to that limit, you get this factorization. It doesn't rely on the fact I considered that specific process. So in other words, you can show sort of the basic properties of a quark emitting a gluon, essentially independent of the hard process that produced it, that this is universal. So let me draw it like that. Just stick with the gluon for now being emitted. And what you end up with is this, hopefully get the factors right. S quark gluon now, or anti-quark gluon if that's what we're interested in. Don't worry too much. It can be either. The splitting function is the same. And these are really arbitrary. It's now an arbitrary QCD process. So this is finally, this is not quite just, let's just dot the I's and cross the T's. So this is not quite what we want yet, because I've made an argument before about the cross section, right? Having this factorized property where I've only talked about the matrix element squared. So we need to deal with the phase space, but that doesn't add too much to the discussion. But let me at least, you know, deal with that. There's also a phase space integral to deal with. But find this also factorizes in that limit. Okay. So in particular, it's not too much work, in fact, just to show this. In the limit, there's some part on I, something very general now, but remember, there's just labels for quarks and gluons. it goes like this. We get some factors of pi as usual because it's a phase space. Sij dz theta ij squared over theta ij squared. And therefore, putting it all together, so n plus gluon equals, in the quark gluon collinear limit, sigma n dz d theta ij, so the angle between them, sum alpha s over 2 pi, and the splitting function as claimed. And so there we have it. And we have a similar, let me write it here. One could do the same thing, of course, for other splittings. So similar factorization for other splittings. So let me just mention that. So one could, of course, have a gluon being emitted for the relevant process, and that angle being collinear, and then you'd have a glue. I write it like that, glue of z. I won't give the explicit expressions. One can find them easily enough. Actually, I think they're in the printed notes. It's not really relevant for us. Just to say that, again, one can do it. And also, of course, a gluon can split into a QQ bar, and that also has universal behavior. So the only difference is that the p's are different. So the only difference is in the p's, splitting functions. And I only dealt with a collinear case, but, and I'm not going to go into the details, but the same type of behavior also seen for soft gluon emission. So I just include these things for completeness. So with a few lines, in our case, one can show this. So as that gluon becomes soft, this also factorizes. So it looks different. It's not a splitting function anymore because it's not a collinear splitting, but one has a universal factor, so-called iconal factor in the jargon, which is a sort of a universal probability for soft gluon emission. I'm not going to use that any more than, but you know, one clearly wants it to happen in both cases if the arguments I made are going to hold. The color connected partons, to be clear. Okay. So let me summarize. So QCD, it has simple and universal factorization properties in the soft and collinear limits. You know, this is required actually by the cancellation of infrared divergences to KLN. So why is that? Again, the point is that this statement holds for kind of general classes of observables, and if one wants that to happen, it needs to rely on something deeper than sort of some process by process thing. And indeed, the cancellation happening in those limits comes from the fact that in those limits, one factorizes off the actual underlying process, the sigma n, and one doesn't care about precisely what it is. And then once that happens, one cannot show that indeed you get this cancellation. That's the kind of idea. And again, these splitting functions which are the probability of emitting collinear radiation. These connect the low energy, allow us to connect the low energy non-perturbative physics to the high energy scattering. So let me say something about that. What do I mean by that? Well, precisely these things play a key role in parton showers. So remember, a parton shower is something which takes you from our quark emitted, say, which calculates perturbative QCD, and then you, in a Monte Carlo, one wants to connect this with what you really see in a detector, which is this collimated shower of particles, a jet, which then hadronize. And so the parton shower does that. Parton shower, I shouldn't call it PS because I've used that for phase space. Parton shower does that. Okay. So why? Well, let's recall. I'll be very heuristic here, but give you an idea of why it's important for parton showers and for doing that connection. Again, let's recall that the quark collinear to the gluon has that form. And it holds, and here is the key point, as I say again, it holds for arbitrary sigma n plus 1, sigma n. So let's imagine doing our shower, okay? So the first step is we've got our arbitrary hard scatter, sigma n. There it is. And then we want to do a parton shower to one of the external legs to do that. So how might we go about that? Well, we start with just the outgoing quark. Well, actually, no, let me say it this way. The first point is that we precisely use the fact that here we want to call that sigma n, and therefore the showering, this collinear radiation, one can happen in a way that's independent of the specific sigma n because of this sort of expression. So the showering of the outgoing quark line should be independent of the hard scatter. So we start with just the outgoing, quark, so there it is, okay? And then we use this. So sigma quark plus gluon is equal to sigma quark integral to z dot 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 p q to q g, okay? So that's our sigma n plus 1, that's our sigma n, and so this thing, one can imagine using that sort of approach, one could emit a collinear gluon. And then the next step is you just iterate it, okay? But then you simply iterate. So sigma n plus 1 now, let's say maybe we'll emit a second gluon. Well, that's going to be this. Sigma n is now sigma quark plus gluon. Sigma quark plus gluon is equal to sigma quark plus gluon integral to z dot 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 quark to quark gluon. And so one can do that, and so on. And the crucial point here is that every step in the way, you've just got a rule which allows you, which could in principle, one could believe, tells you how to emit the gluons, what probability, but crucially that this rule, when in the end you end up with something which will have lots and lots of things being emitted, you don't need to actually calculate that entire process. One could just iterate this rule, and that's the idea. So the parton shower provides a systematic way of doing this. I have missed a lot of the details of how this actually works in practice, but that's the basic underlying idea. So it's a systematic way of doing this iteration, let's say, and therefore giving a collimated shower of QCD radiation. Sorry, I'm fitting in there. A jet, and also soft emission. Not forget that. You can also account for that, although I've not said anything about it. And so again, this sort of thing goes to all of that without ever having to calculate, sigma n plus, sigma quark in this case, plus n gluons, plus m quarks, plus k antiquarks. It could be a complete nightmare. You never even consider trying to do that, but only the parton shower and this factorization allows you to do that. So only possible because of this. Now, there's a lot of caveats there. First of all, the above discussion, as I just said, is very heuristic. So I've really not said actually procedurally how this works. And those are important things, not things I'll go into here. So we've got this angular integral, and you can see here that this thing is clearly blowing up. And yet I've sort of waved my hands and said, well, we use that as a probability for emission. So how do you actually do that? How do you actually use this technically? I've not gone into that. Certainly at some level you would cut this angle off when it gets too low, and that would get you into the hadronization stage. So that's not actually infinite. But even before that happens, one wants a thing which actually iterates this in the correct way. And that I've not got into how that works, but one can do it, but it still, as I say, relies on this factorization. The other thing is that, of course, this doesn't get you everything. The shower only gives you a good approximation to exactly this collinear and soft emission. So it doesn't put higher order people who work on higher order calculations out of business. It doesn't give you the general expression for this, clearly. It's just in that soft and collinear region. And so for e.g. E plus, E minus to Q bar plus gluon, in a 3-jet event where these are really separated, you need the full calculation. And finally, at NLO and beyond, there is overlap between the actual sigma NLO, so that sort of thing in our case, and what is generated by the parton shower. In other words, if one started a leading order with that and then did a shower that took you to that. And so one has to be careful to avoid double counting, and there's ways of doing that. So that's another thing to bear in mind. I might say a little bit about that later as well, if there's time. Okay, very good. So let me summarize a little bit about that as well. So I've discussed it in infrared. Let's say a bit about infrared safety, some more general statements. So I've discussed these infrared singularities or divergences. cancellation in E plus E minus dihadrons. And then I kind of stated the KLN theorem, which said for suitably defined observables or something to that effect. So what does that mean? So when more generally will this occur? Well, the answer isn't always obvious, but one can at least develop rules which will tell you, if your observable, whatever it is, passes these things, then one expects it to kind of obey KLN, to be not sensitive to long distance physics, if you like. So in other words, what questions can we ask of our theory? So the basic idea is that, well, in a nutshell, we don't want sensitivity. It's maybe slightly obvious, but that is the idea. We don't want sensitivity to soft and collinear emission, in other words, to long distance emission. And before we saw specifically that, for example, the real diagrams alone were certainly sensitive to that, but the sum of the virtual was not. But let's formulate that a little bit more. So the observable should be invariant under these sorts of branchings. So PA goes to PI, P goes to PJ plus PK, with either PJ collinear to PK or EJK goes to 0. And formally, we require some observable, so that's an observable. That's what the O means. Of P1 dot PI, PJ dot. If I goes collinear to J, this should just be the observable as before, but of the sum. And if similarly, that's the same, but now if, let's say, EJ becomes soft, again, it's just the same thing. It should just be the sum. And that should happen smoothly. Oops. So we've seen that this happens in E plus E minus, let's say to QQ bar gluon, once we suitably include all diagrams. Again, it doesn't happen otherwise. And so that's one example. But there are many other things which, other examples one can give. So what is not infrared safe? Number of partons, that clearly isn't, right? If one just emits another collinear or soft parton, that's clearly going to change your observable in that limit. So it can't possibly be infrared safe. As we'll see, functions of the incoming momentum, but more of that later. So let me say no more about that. Write it down. More later. Some older jet algorithms, in fact. Say more about jet algorithms later. And see the problems. So one of the problem sets will be precisely on discussing these things. And of course, it's useful to also discuss in your tutorials in more general terms the kind of things that won't or will be infrared safe and why those are. And let me say that I'm talking about sometimes or even often one distinguishes in your terminology between collinear and infrared safety, where in that case, collinear would mean sensitivity to collinear radiation, and infrared safety would be sensitivity to soft radiation. But here I just mean both of them, and I'm giving that the title infrared safety. Okay, that's just if you see that elsewhere or have seen it before, not to be confused. It's just a notation thing. Okay. So let me say one more thing very briefly, because I should at least deal with it, which is this question of, talked a lot about infrared divergences. Let me at least say a little bit about the ultraviolet. You've learned about this a bit in your QED and QCD course, but let me say a little bit more. But I won't go into too much detail. But okay, in QED, QCD, we get ultraviolet divergences from loops. So something like this again. It's just the same sort of loop diagram, right? It's L, D4L, and that, let's say, goes like DL over L. And now clearly from the upper limit there, as well as the lower limit, one has something that goes off to infinity. So ultraviolet just means the high energy limit of that integral. So this, again, this is completely distinct from the infrared. It's the completely opposite energy regime, and the solution is completely different. It only happens also in loops. There's no ultraviolet divergence here associated with real radiation. And it's something which tells you about your theory, which in particular it tells you about the fact that as you formulate your theory naively in terms of your Lagrangian and things you put in there that you say, oh, that's the mass, that's the coupling, that one has to be careful about really saying what those things are and actually assigning them an experimental value. And doing that systematically when in your theory itself, one can include loops which themselves depend on the couplings in order to calculate an observable is a tricky thing, and you need to do that systematically. And so when the bottom line is that your theory expressed in terms of your parameters in the Lagrangian might be divergent, but if you re-express things that you're only ever expressing one observable in terms of another observable, that's what renormalization is, and that gives you finite results. But you learned a little bit about that elsewhere, but just to remember, recap that. So indeed, so here, really without going into the details, we fix via renormalization. But it's not a trick, it's just a, it's just a fact that as long as you're really expressing your theory, or you re-express your theory such that your inputs, what we call bare parameters, are actually related to observables. And then your predictions are really relating one observable to another, and then everything makes sense and everything is finite. But as we know, this leads to a scale dependence. In alpha S, d alpha S, d log mu r. So we've seen a little bit about this already. Sorry, let me write that again. Which is just the beta function, that's the definition of it. And this is, one can calculate in that way, where this is equal to when the dust settles, that. And there's a lot going on in there, and it's a rather complicated calculation, but one can at least see that one's got an NF, which is the number of active flavors. And so that certainly comes from that sort of diagram, which you have in QED. And if you just had that, or if indeed the number of active quark flavors was large enough, the sign of this thing would be positive. It turns out that's about 16, so we're certainly far away from that in QCD. But that's certainly what you have in QED, right? And there the energy behavior is no longer asymptotically free. But all of this stuff comes from, these sort of diagrams, etc., things that are only there in QCD. So really because of the non-abelian nature, the fact that the gluons self-couple. Okay, so this is less than 0. And so the solution is that alpha s at some scale mu f, not factorization scale, just some final scale, if you like, is equal to this. And therefore alpha s decreases as mu increases. So I'll show you a few slides on that in a second. But before doing that, let's just say a little bit more about this from the sort of procedural point of view, if you like, or the collider phenomenology point of view, which is, the question is this: so what to take for the renormalization scale in some given process? So you may well have heard, if you're familiar with this stuff at all, that one should take it to be of order, the sort of hard scale of the process. So why is that? Well, let's consider, give you a flavor of why that is. Let's consider, e.g., some, well, not e.g., let's consider some arbitrary observable, depending on a scale q. So that will literally be q in DIS. I'll talk about what that is a little later. Or, you know, whatever MZ in Drell-Yan or whatever it is. And let's say that this begins at order alpha s. I mean, that's just because that's the way I've set up the discussion below. That's not crucial. And it's calculated to order alpha s squared. Okay, so NLO. So this has the form. Let me do it in red. There's our observable. Going to be O1 alpha s, it begins at order alpha s. Then you're going to get something which looks like this, O2 minus O1 B0 log u squared over q squared. So that is what you would get if you did the calculation. And therefore, the observable, the rate of change of the observable with whatever you take from mu, the renormalization scale, is equal to O1 d alpha s d log mu squared plus d alpha s squared d log mu squared times O2 minus B0 O1 log mu squared over q squared minus alpha s squared O1 B0. That cancels with that because I've got it written up there. Then we've got that, let me stick with the red, in fact, and therefore DO2, sorry, DO, d log mu squared, it just goes like that, which goes like order alpha s cubed, okay? And so the mu r dependence, let's call it mu r dependence, that's implied above, is one order higher than the calculation order, which remember is order alpha s squared, okay? And therefore, first of all, scale variation uncertainty, just by varying the scale a bit, can be used as an estimate of the uncertainty due to these missing order alpha s cubed terms. So the uncertainty due to the truncation of your perturbative expansion. And that seems a little hand wavy, and indeed it is. It's really just a rule of thumb. But it gives you some estimate of these things. In particular, the more orders you calculate, the smaller the effect of varying mu will be. So you get a smaller uncertainty, and that's certainly natural when you're calculating these things perturbatively like that. But let me say a little bit more about that, though, because what am I varying about when I say vary it? Well, in addition, if we take mu squared is a lot bigger than q squared, or mu squared is a lot smaller than q squared, or mu squared is a lot bigger than q squared, then, you know, the log there is going to be a lot bigger than 1, and alpha s log mu squared over q squared is not small. And so we go back to our perturbative expression there, and now suddenly, rather up here, if one takes mu squared too far away from q squared, the next order up in the calculation can actually become bigger than the first order in the calculation, and so on. Certainly doesn't have a sensible perturbative expansion. So you need, that's fundamentally the reason why you have to take mu squared of order q squared, for the series to be nicely convergent. I.e. the last, each order genuinely smaller than the last. And in particular, if you do take mu squared of order q squared, that's the key point, then one does have that. Then the next order here, the alpha s squared term, is genuinely a lot smaller than the alpha s, and then likewise for the next one up, and then that one therefore expects the all order result, the left-hand side, if one were to really calculate all orders in the perturbation series, to be, you know, at least pretty close to those first two terms. So in other words, if you take a value of mu squared that's very far away from q squared, and therefore that brings you very far away from that nicely behaved case, one's also taking you very far away from what one expects the genuine, you know, all order result on the left-hand side to be. So again, it will, if one took mu squared to equal 10q squared or 100q squared or whatever, if your calculates it enough orders, actually you'd find that things would stabilize in theory, and you'd get a reliable result, but this would happen very many orders up, and before that you'd be jumping around all over the place. So that's the kind of idea. So let me show you a few slides to that effect. I'll give you an idea of that. So first of all, here we've got on the left-hand side the kind of theoretical prediction for the running of the coupling, and you can see, sure enough, that it decreases at increasing energy. But then on the right-hand side, we've got the data, you know, shown against that, and one can see quite clearly that it's sort of lying on top of that prediction very nicely. So what is this data? Well, there's a lot of it. Coming from all sorts of different sources. We can have things like tau decays. One calculates that to lots of orders in QCD, and therefore is sensitive to the value of alpha s, the strength of those higher order corrections. Also structure function data, PDF bits. I'll say a bit about them in a second, in fact, or rather in the next lecture. And also lattice QCD, so one can input a value for the alpha s into your lattice calculation of things like hadron masses, and essentially tune to that and get out a rather precise value from that. And this all comes together in that global fit, or that global value. And the other point is about the scale dependence. So just to illustrate really what I'm talking about here, I've taken more or less at random a process that's been calculated to many orders in alpha s, in particular Higgs decaying to glue. And so that's represented here. So it's actually the sort of amplitude times the complex conjugate, and it's slightly similar to that diagrammatic, in fact, the same as that diagrammatic way of representing things I showed you in the first lecture. So anyway, the point is just that there are lots of loops going on in here. And so what we've got here is the NLO, NNLO, and cubed LO, and then 4LO results as a function of the scale that you input, so precisely that renormalization scale in JEV. And one can see a couple of things exactly illustrating what I'm talking about. So in particular, first of all, one gets in the NLO case a very large scale variation. Let me just get rid of that, and you can see that happening there, right? You know, as you vary the scale, but as you go up in the orders you calculate at, that becomes smaller. You get a smaller variation there, smaller again, and then even smaller again in the red case. So that's showing you that if you had some uncertainty by varying the scales, one would get a sort of reliable-ish estimate of the actual uncertainty you have from the missing higher orders. And the other point to make is that You know, once you can go to N4LO, it kind of doesn't matter if you take your scale as, if you take your scale as sort of 300 JeV or something like that, or if you take it at Higgs mass, which would be a more sensible thing because it sort of stabilizes. But if you did that at NLO, you would be way off if you took something well away from the Higgs mass. And that's those large logarithms coming into play. So you really jump around in your perturbative series and it's not very convergent. Okay, so I'll stop there and for this lecture.